Hi, I'm Stephen. I'm going to talk to you today about integer vector optimizations, specifically auto-vectorization, and how it's affected negatively by usual arithmetic conversions in C and C++. So to start, I'll just describe what usual arithmetic conversions are. In C and C++, when you perform an operation on variables of type char or short, they're automatically promoted to type int for the operation to be performed. So in this example here, the chars A and B are automatically extended to i32. The add is performed as an i32, and then the result is subsequently truncated back to i8 to be stored in C. And this is exactly what you would expect from a C and C++ program. But imagine for a moment that A, B, and C were arrays, and that this particular piece of code was the body of a loop iterating over those arrays. So for any element of A and B, you add them together and assign to an element of C. In these kinds of cases, what we were expecting to see for our platform, which supports 128-bit vectors, is for the vectorizer to kick in and start selecting V16I8 vectors for these kinds of operations. But that wasn't happening. And we did a little digging, and what we found was that the semantics of the source language that the front end has to honor was preventing the vectorizer from doing as good a job as it could. So our solution was to write an IR level pass that removes these extend and truncate instructions. So essentially to do this. And this way it allowed the auto-vectorizer to actually start selecting, say in this example, V16I8 instructions to be vectorized. Of course, when you're doing this kind of transformation, there's a bunch of criteria that need to be met before you can say that this is absolutely safe to do. And there are certain kinds of instructions that you can or cannot transform. And I'll just use this case as an example because I can't go into detail on all of the different criteria now. But we know that in this example that with modulo arithmetic, specifically with signed wraparound, we know that the code on the right will produce the same result as the code on the left for any given inputs A and B. And that's something you'll notice has changed, is that the NSW, no signed wraparound metadata, has been removed from the add operation. So thanks to this signed wraparound, we know that it is safe to perform this transformation. And once we had enabled this pass in LLVM in our own compiler, we found that the vectorizer was vectorizing way more examples than it had been previously. And these are the kinds of results that we were seeing. A lot of these came out of the TSVC benchmarks. So you can see there's some great ones there, 30 times faster, 20, 10, 5, 2 times faster, which is brilliant. But on the flip side of that, there are also some regressions. Specifically, those 2x slowers and the 10% were concerning to us. And we did some more digging into this, and we found that because we're removing instructions, we're removing the extends and we're removing the truncates from basic blocks, the cost involved in inlining and loop unrolling had changed. So the inliner and the unroller were doing different amounts of work that was actually causing these performance regressions. So in a lot of these cases, we were able to go by a case-by-case basis and use things like pragma unroll and to force inlining to manually adjust these kinds of these regressions. And in a lot of cases, we were able to completely reverse the regression we were seeing. So now, really, that's all that's left for us to do is to actually address this in LLVM by adjusting the heuristics involved in inlining and loop unrolling. And once we have addressed these issues, and we're happy we've addressed these issues, we hope to push this pass upstream because we think it should benefit anyone who has a vector unit in their target. And that's all from me. Thank you.